Okay guys, so today we're going to look at slope fields. So the first question says, what family of functions solves the differential equation dy dx equals cosine x? Graph several solutions on your calculator. Okay, so a differential equation is any equation with a derivative. And a solution to a differential equation is a function that has the given derivative. So we know that any function of the form y equals sine x plus a constant will have cosine as its derivative. So if we were to think about the graphs of all the possible solutions, so the graphs of all the functions that have cosine x as their derivative, right, it would just be the sine graph, right, the standard sine graph, shifted vertically up and down. Just be the same shape over and over again. Okay, so let's look down at this explanation. We know what family of functions has cosine x as its derivative, so we can solve the differential equation and then make a graph of its possible solutions. We may be unable to solve some differential equations. So for instance, we may have something like dy dx equals e to the x squared. We can't solve that and get a function, like just an explicit function that has e to the x squared as its derivative. But even if we don't have like an exact formula for the function, we can still get an idea of its shape. So since the differential equation gives the slope at any point xy, we can use that information to draw a small piece of the linearization at that point. So just a little line segment that has the same slope as the function, which approximates the solution curve. Okay, so let's just see what that means. We want to construct a slope field for the differential equation dy dx equals cos x. So when x is 0, the slope here is 1, because the cosine of 0 is 1. So we're going to draw little line segments that have a slope of about 1. We'll just do the best that we can when x is 0. Okay. Let's just say that we're counting by pi over 2 along the x-axis. And then pi and 3 pi over 2. Okay. So now the cosine of 90 is 0. So then here, our original function has a slope of 0. So we're going to draw little line segments that have the same slope as our original function. All right, then when x is pi, the slope is negative 1. So we're going to draw little line segments that have a slope of negative 1. When x is 3 pi over 2, the slope is 0. Right, so we're going to go like this, this. Then we're going to do like the same thing on the left. So when x is negative pi over 2, cosine at negative 90 is 0. So again, I'm just going to go like that. Okay, so in this way, we're getting, like, we have all these little line segments that have the same slope as the original function, the function that has cosine x as its derivative. So we could actually then just pick a point like 0, 0, and try to like trace out, okay, and I know it's not perfect, and try to like trace out, and my lines aren't perfect. I have a better graph on the next page. But we can basically follow along and get a picture of the shape of our original function because we know its slope at all these different points. So let's look at a better picture. Okay, so in question 3, they're telling us this is the graph of a slope. This is a slope field. So the little line segments at each point have the same slope as the original function. So they want us to draw a smooth curve through 0, 0. So 0, 0 must be a point on our original graph. And we're just going to try to trace out like the shape of our original function. So we can see this is the sine curve, and its derivative would be cosine x. All right, so let's look at 4a. We want to construct a slope field for dy dx equals x. So when x is 0, the slope is going to be 0. So we're going to draw little line segments that have a slope of 0. When x is 1, our slope is going to be 1. Just keep going like that. Right? When x is negative 1, our slope is negative 1. Okay, I could keep going, but let's just think about this. Well, let me do one more. So when x is 2, our slope would be positive 2. Just make it look a little steeper. And when x is negative 2, our slope would be negative 2. So if I were to trace out like a particular solution, just one solution, okay, I would get that my original graph is a parabola, right? And that makes sense since the slope is x, our original function must be like x squared. Okay. So now, guys, let's look at the next one. We have dy dx equals y. So try to pause the video, take a minute, draw the slope fields, and then go on to C and try to make a generalization based on what you've seen in A and B. Okay, so pause it for a second. Okay, so sorry. So let's look at this. So when y is 0, the slope is 0. So all along here, the slope is 0. When y is 1, the slope is 1. So all along the horizontal line, y equals 1, the slope is 1. When y is 2, the slope is 2. Okay, so you can kind of get the idea here. All right. Now, to make a generalization, we can see that if the slope depends solely on y, then the slope is going to be constant along each horizontal line. If the slope depends only on x, then the slope will be constant along each vertical line, right? When x is 1, the slope will always be 1, or something like that. Okay, so let's go over to the next page. Because again, like, this isn't really that hard. You don't have to be exact. But let's look at number 7, which was an AP question. So we can find the slope of the original function at any point. So let's start with 2, 0. So when x is 2 and y is 0, to find the slope at that point, I plug in 0 for y and 2 for x, and I get a half. So the slope of my original function at this point is a half. Okay, so it's going to be kind of steep, right? We go over 2 and up 1. Just keep going like that. So all of this is posted on Edline, and I want you to do the entire worksheet, and I'm just going to give you a few hints because there are a bunch of matching questions where you're given the equation for a differential equation, just like we have in 7, and then you're given maybe like multiple choice. This is what the AP does a lot. And you have to pick out which of the slope fields matches the equation. So let's just think of how we can figure that out, some tips. One thing to do is look at what we already talked about. Look at, do the slopes depend solely on the x values or solely on the y values? Right, like if you see, oh, the slopes are always the same when x is 1 and the slopes are always the same when x is 2, right, you're looking for an equation that only has x's in it. All right. Another thing we want to look at is where is the slope 0, right? It's going to be pretty easy. So look for 0 slopes. It's going to be pretty easy to see from the equation, okay, where should the slope be 0? And then where is it 0 on my graph? All right. Also look along the x-axis because you know that there the y value will be 0. And 0 is an easy number to plug in. Often it'll get the slope to be 0. Also look along the y-axis because there the x value is 0. And again, it can be easy to like plug in 0, can, you know, sometimes make the slope 0. It can just be easier to look at. Also, last tip, look at where the slopes are positive and look at where they're negative, right? So if we had something like dy dx equals x over y, the slope should be positive in quadrants 1 and 3, negative in quadrants 2 and 4, and then undefined when y is 0, and 0 when x is 0. So, all right, guys, please finish the packet. Good luck with it.